you ready?
Yeah.
Okay, we start now.
Okay. Hey everyone, my name is Amrit, and today I'm going to tell you a little bit about one of the biggest mysteries in our universe, that of dark matter. Now, I use the technique of gravitational lensing. As you can see in the schematic on the right, gravitational lensing is simply a phenomenon predicted by Einstein's theory of relativity. All it says that anything with mass bends the path of light. So as you can see here, if you were looking at a distant galaxy, the light on its way to us on the Earth, it might pass near a neighboring galaxy, and the mass from this galaxy would bend the light. Now, I'll show you how this would produce spectacular images when we look at things through telescopes. But first, if you decide to fall asleep in my talk, you can find more about the research on the cover of Nature Astronomy for the June issue, where my research was published. And Nature also wrote a news and views about our article. And our article was actually in the top 1% of all articles published across all journals for how much attention it generated. So there were more than 70 different news articles written about it, and it reached over 1 million people on YouTube educational channels. Now that's enough about me. Let's all look at a pretty picture of our universe. You're looking at a galaxy cluster. A galaxy cluster is simply a family of galaxies that are bound together. Now the members of this cluster are what you see as the yellow blobs. Everything else you see, all the other colors, including all the tiny dots that you see in the background, they are background objects. Now each dot is an individual galaxy, and it has 100 billion stars, just like our sun. So you can imagine the scales involved here. Now, the story of dark matter begins in the 1930s with Swiss astronomer Fritz Zwicky. And when he looked at observations of galaxy clusters, he found that for these galaxies to be bound together, to stay in their little family together, you need a lot more mass than what you can see with the visible light. Now you fast forward about 40 years in the 1970s, and when astronomers looked at individual galaxies, like you see here, this is our neighboring galaxy, the Andromeda galaxy. Now every dot here is one star, or a cluster of stars. Astronomers found that to explain the speeds of these stars zipping around the galaxy, you need a lot of invisible dark matter. Today, with observations of the cosmic microwave background, this is a relic of the Big Bang, the creation of our universe. We now know that dark matter comprises a staggering 85% of mass in our universe, but we have no idea what it is. The best thing astronomers can do is draw pictures. So if you see the schematic here on the right, this is a drawing of a galaxy. And we think now that all galaxies and all galaxy clusters are embedded in a sort of halo. We call it a dark matter halo. So you can see here this kind of blue spherical blob. So that's how we think dark matter is distributed. Now this is one of the biggest problems in physics, along with dark energy. Why is that? Well, the standard model of particle physics, this is a pillar of modern physics. The other pillar is Einstein's relativity. The standard model tells us how 3 of the 4 fundamental forces in the universe work. And it predicts a range of particles, but it's incomplete because it doesn't predict a particle for dark matter. Now the standard model also has other problems, and as a result there were different theoretical extensions which predict particles that try to remedy these problems. Now the leading candidates for dark matter from these extensions are either ultra-massive particles, called WIMPs, so they're very massive, or ultra-light particles, called axions. Now, you might imagine the identification of the correct particle will help us rule out an entire class of theories while pointing the path towards new physics. Now, despite decades of searches and billions of dollars of funding, we are yet to detect WIMPs in laboratory experiments. In my thesis, I asked whether dark matter can be made up of axions. Now you might be wondering why it's called axions. The person who predicted this particle won the Nobel Prize in 2004, and he proposed it to solve another problem in physics, not dark matter. And he walked into his kitchen and he saw this detergent lying around, and because this particle cleaned up a problem in physics, he decided to name it axions. So now, I'm sure you've seen this in Wellcome or Park and Show. Now you know the detergent came first and the particle came second. All right, gravitational lensing. Lensing is really just the focusing of light rays into multiple images. You can imagine this is sort of like looking through a magnifying glass. If you had a distant galaxy, you see this white blob, on its way to us, the light from this galaxy on its way to us, it might pass near another galaxy, the yellow blob. Now, because of this lensing effect, because the light gets bent, you're actually going to be seeing multiple images of the same background object through your telescope. Now, the image on the right there is a real image taken with the Hubble Space Telescope. And you can see 4 bright white points. So they're the same object being lensed multiple times. In the center, it's the lensing galaxy, which is a yellow blob. Now, this phenomenon lets us really probe the structure of dark matter within the lensing galaxy, within the yellow blob. Well, how does dark matter distribute itself? For WIMPs, like I said, it distributes itself very smoothly, like this blue blob that you see. For axions, the first simulations were done in 2014, also by our collaborators, featured on the cover of Nature Physics. And you can see that the patterns are very structured. There's a lot of interesting stuff going on. Why do these patterns happen? Let's remind ourselves some high school physics. When 2 waves are in phase with each other, they undergo constructive interference. When they're out of phase with each other, they undergo destructive interference. Now you can imagine this is sort of like waves on a beach, or if you throw a pebble into a pond, it creates ripples. That's because of interference. The same reason is why you have these very nice patterns, because axions, they're very light particles, and there is a concept in our universe called the wave-particle duality. Everything's a particle and everything's a wave. You're all waves as well. Now axions are very light, so their wave behavior is very powerful, and so that's why they're also called wave-like dark matter. But that's the reason you see these very obvious interference patterns on astronomical scales. Now, if I were to make a plot of the magnification field, this is simply how much the light gets magnified by. This is what it would look like for WIMPs. The color tells you how much the light gets magnified by, and then so the regions of highest magnification typically form this ring-like structure that you see here. Now you see that it's very smooth for WIMPs, right? What about axions? Well, in my research, I find that axions actually create a very complicated pattern. They create this wavy, corrugated structure for the magnification map. Now, to understand better why, let me zoom in to a small region of the magnification field. On the left here, you're seeing the zoomed-in magnification contours in the black lines for the WIMP model. The background colors are the mass distributions. So as you go towards the center of the galaxy, it becomes heavier. So that's why the color is red on the right side. Now you see the mass distribution for the axions is actually quite complex. It's got a lot of structure going on. In the third panel, I've shown you just the fluctuations that arise from the interference between the particles, so you can really see the structure better. What happens if I put the magnification contours on top? You can see that the magnification pattern actually directly corresponds to the fluctuations in mass density. Now this is cool and all, but we don't really see these with telescopes. What we see with telescopes are lensed images. So how do lensed images look? Well, I'm plotting here for you the lensed images predicted by WIMP model. Now you can again see the magnification contour is very smooth, and the lensed images are actually the 3 white arclets that you see with their centers marked by a red dot. Now for axions, because of this complicated structure, you can actually see the images. They've moved. They've been displaced from their original positions. You see that their positions have changed with respect to the red dots. If you look a bit more closely, you'll also see that the sizes of the arcs have changed. In lensing, size means magnification. That means the brightnesses of these images have also changed. Now why is this interesting? Well, something I didn't tell you is there's been a 2-decade-long problem in astronomy that has plagued the lensing community called lensing anomalies. When astronomers look at observations of gravitationally lensed systems, you can see spectacular images here taken with the Hubble Space Telescope. They find that when they use WIMP lens models, they're unable to reproduce the brightnesses and positions of most of these images. Now you can see that qualitatively, axions might be able to be a solution to this problem because they can move images about, right? Well, this is science, so we need to do more quantitative tests. And that's what we do. First, I'm showing you a statistic called the position anomaly. All this is simply how well your model can reproduce the positions of lensed images. The prediction for axions is the orange dotted line. The observation not from one system, but from multiple different lens systems are shown in the gray histograms. You can see that the axions can produce the trend very well. What about the brightnesses? Same thing. Now, this is statistical agreement because it's many samples, right? It's a general agreement. And if you're not happy, fine, I'll do a more stringent test. we pick a specific individual system and ask, can axionic dark matter reproduce these observations? What you're seeing here is 4 panels. These circles correspond to the positions of the observed lensed images. The sizes of the circles corresponds to the measurement uncertainties. Now, if I make a WIMP dark matter model, these are the predicted image positions, the plus cross signs. And you can see that in almost all the cases, they are unable to reproduce the positions of the observed images. What happens if I make axionic dark matter models, represented by the dots here? Now we need to make a lot of models because I told you the interference patterns, they're random. So you can't just have one model, you need many models to see what their effect is like. And you can see that axionic dark matter in all the cases is able to reproduce the observed positions of these lensed images. Now of course we do more tests. We look for the brightnesses, can it reproduce brightnesses? We do a ton of tests and we find that axionic dark matter passes all the tests, while WIMP dark matter models struggle to do so. That brings us to the conclusion. For the first time, we resolved this 2-decade-long problem of lensing anomalies. And the good thing is, the mass of the axion we test, it's supported by other astronomical observations, not from lensing, from other features. They support the same particle mass, so that's always a good thing, right? Now this work has started a new area of research where people use gravitational lensing to study axionic dark matter and help us learn more about the nature of dark matter. Now of course the work we're doing and will continue to do in the future with collaborations is use the wealth of data with new telescopes, using the world's best telescopes. If you heard, the James Webb Space Telescope launched just a bit more than a year ago. We'll be using that. We'll be using the Hubble Space Telescope. And what this will really help us do is, in the next few years, it'll tilt the balance between WIMPs and axions and point towards the correct path of new physics. Now, if you fell asleep and you're just waking up, if there's anything you want to take away from my talk, the first thing is that the work we're doing is to shine light on the path to new physics, new fundamental physics beyond the existing pillars of physics, like I said, the standard model. The second thing is, if you're wondering how this affects your day-to-day life, you don't really care, right? If you're not an astronomer. Well, imagine fire, imagine electricity. When humanity first discovered these things, we didn't really know what their impact was going to be. But today we know, for example, electricity is a founding bedrock of the human civilization. The same way, dark matter takes up 85% of the universe and we don't even know what it is. So you can imagine dark matter has the potential to be the next stepping stone for humanity to become a spacefaring civilization. With that, I end my talk. Thank you.
Thank you. Thank you for your talk. Now start with the Q&A now. Any question from the floor?
Thank you. So I'm a biologist, but I'm also very interested in astronomy because I use a lot of imaging techniques as well. So for WIMPs and also axions, one is ultra dense, one is ultra light. Is there something in between that is other theories that is still like there is a three-way balance that is still debated by the physics community? Thank you.
Thanks for the question. There's a range of particle masses that have been predicted. It's just that the leading candidate is WIMPs, the current paradigm for the past few decades. Axions are an up-and-coming candidate. There's particles with masses between these. These are very light at the extremes of the mass scales, right? And the laboratory experiments people do right now, the particle physicists, for example, at CERN, they usually look for WIMPs because it's still very difficult to look for axions, ultralight particles in laboratory experiments. So there's people still searching, across a wide parameter space for these particles. And there's a lot of different theories. So that's why using astronomical observations is very nice because we can rule out entire classes of theories even without detecting the particle because they need to fit the astronomical observations. Yeah, thank you.
Any more questions?
So if I'm understanding properly, in the WIMP dark matter model, you have very specific predictions for the locations of the lens images. Whereas in the Axon dark matter model, because of these random fluctuations in the wave dark matter field, you end up with basically a statistical distribution of possible positions, essentially. So my question to you is that very satisfying to you? I mean, because essentially what you have is that you have a greater uncertainty in where the positions of the image might occur. And so because you have now a model which allows for greater uncertainty in the position, you have agreement with the observations. And so I'm not disparaging the Axion dark matter model, but is this a very, I mean, it seems that you just have a new model which allows for greater uncertainty in the position. Is this satisfying to you? Do you know what I'm trying to ask?
Right, yeah, thanks for the question. It's kind of got the same feeling as accepting quantum mechanics. Quantum mechanics is not very satisfying to a scientist because it's probabilistic in nature. That's why Einstein hated it his whole life. So the same way, if you make WIMP models like this with crosses, there's no way that you could make the crosses fall within the circles, within the WIMP paradigm. So that's a very severe problem faced by the theory. Now, on the other hand, because, like I said, the random fluctuations, there's a larger spread in the predictions. But the best way to rule this model out is just to have more data, and where you have more systems with many different lensed image positions,
Right.
and there will be a case where even the random spread can't describe the observed image positions. So the only other way to really be more satisfied is have more samples, more data sets.
Great response, thank you very much.
Yeah, thank you.
Any more question?
Thank you so much for the talk, and it's really nice for you to have publication on Nature. And I would like a simple, really naive question. So all the Hubble, JWST telescope, they are like space-based, and we know that for example, United States, they are building proposed to build TMT, and also like GMT in Chile right now, and they're ground-based, and they are like 30 plus minus meters for the aperture. So will they shed light for the research for those dark matter stuff, or?
Yeah, thanks for the question. Definitely, all the new telescopes that are being built will be observing gravitationally lensed systems. That's sort of the hot topic right now in astronomy. Even the James Webb Space Telescope, one of its main science goals is to look for gravitationally lensed systems. I didn't tell that to you here, but one of the reasons people look for lensed systems is because they want to see very distant galaxies, deep into the universe, closer to the Big Bang. So that's another application of gravitational lensing. It's not just for studying dark matter, it's for doing cosmology, understanding where we came from. So all these new telescopes will be observing lens systems. They'll all be applicable, putting dark matter to the test.
Thank you so much.
Yeah, thank you.
Okay, time's up for the Q&A session. Now we start the second presentation.